This is video 11B using VL53L1X for a distance ranging on an ESP32 Roam board and an STM32 MicroPython and the BlackPill. The code for this video is at the GitHub site. The information presented in these videos on MicroPython should work as well on any STM32 F4 board. All code examples have pin definitions at the beginning of the file to allow the programmer to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like, as that really helps. In this video, we use our STM32 BlackPill microcontroller on the STM32 F411 car baseboard with an external VL53L1X board to perform short distance ranging. The VL53L1X is similar to the VL53L0X sensor we discussed last time, but it's a newer model. It has a tiny invisible laser that can measure distance to an object, this time up to 4 meters. I wired the VL53L1X device in the similar manner as the VL53L0X. However, I had trouble working with it. I only got the readings if I modified the driver slightly and then did a soft reset of the Thony program. For the readings that I got, they looked more consistent than the older device. Despite a lot of research, I never got a smooth execution of the program. I was troubled by the hang driver, so I used a Saley logic analyzer to research the activity. I thought you would be interested in how I did the analyzing and what I learned. I placed a copy of the datasheet at the GitHub site for the video. I used the analyzer with the car baseboard as it has convenient pins to connect the analyzer microhooks. As the sensor uses I2C, the wiring is straightforward. The driver I got from a search at GitHub. The author had simplified the driver and used it successfully on a Raspberry Pi Pico. The VL53L1X sensors are new boards from a supplier in China. So I tested the sensor with Arduino code and this worked well. Let's look at the MicroPython code. Most of the work is performed in the driver. The test code is straightforward. I did end up adding a function in the code to clear the interrupt, as I found this was performed in the Arduino. I spent time researching the MicroPython driver code, which became useful when I looked at the analyzer data. Here are the 5 actions in the driver. During initialization, the device is reset. It reads the model ID to ensure it's expected, and then writes almost 90 bytes of configuration data. The commands were identical to those used by Adafruit and the manufacturer's code. Okay so far. During the test program loop, the device sends a read command. It receives 17 bytes, and byte 13 and 14 contain the distance value. Let's look at the read command in the analyzer. Here you can see the oscillation of the SDA and SCL pins. SDA is the top chart. SCL is the clock pin and it oscillates for each bit. The SDA pin oscillates to form hex values. The analyzer nicely transforms these into a value displayed in the yellow strip near the top of the graph. From the driver we know that the first byte is the OK status from the VL53L1X device. Byte 13 is a hex 01. And the driver left shifts it 8 times to get 256. Byte 14 is hex A7, which is 167 decimal. The sum of these two is 423, which is good. When I subtract 20, I get a reading of 403, and the target was 400 millimeters actual distance. I do this because the driver value was always 20 millimeters high. Next, let's look at the init. These are the data writes sent by the driver to registers with the device to initialize it. I found the init values to be consistent with what the driver sent. The init was also similar to what Arduino sent. I did see comments by the manufacturer that most of the bytes should not be altered, but several registers could be. And this is how I found the register that clears the interrupt. Unless I included this, the device crashed. Also, I noticed that the Adafruit driver author did the same. Looking at the chart, the clear command immediately causes the interrupt pin to go to 0 for a few milliseconds. Here's the output in Thony. To get the data values, I had to click the red stop button, which is a soft reset. But I only had to do it once. Then I got a value. In summary, the sensor is fast and affordable. It works well with Arduino code. It works with MicroPython commands as well, but the need to manually reset the program means I cannot use it. When I asked the MicroPython forum about this, they suggested that I needed pull-up resistors on the I2C lines. I could see the resistors on the board, and anyway, when I tried adding my own resistors, the board just crashed again. So I will continue to research and report back what I learned. Hopefully you'll have a better understanding of the benefits of a logic analyzer and a brief demo of its use. In the next video, we will look at an RTC DS3231 board. Thank you.